Yeah, I think there's one more spot here in the middle. And yeah, okay, I guess you'll figure out the rest. Okay, so welcome everybody. This is the Scalable machine learning class. First class I've held in Berkeley. I may be a little bit green in the beginning, so I need to rely on you and your feedback also to make sure this is going to be a fun class for everybody. So the first thing that I need is 2 volunteers. So the reason why I need 2 volunteers is because I need scribes for this class. And the scribes, okay, so the scribes won't have to do it for free, so they get 3% of the class equivalent by doing scribing. I need 2 of them, just in case one of them gets run over by the truck. We still have good scribes notes. Okay, and the job of those scribes is to A, produce good scribe notes, secondly, to take notes during my class and make a note whenever there's a typo on my slides. And I'd like to get those notes to incorporate them before I put the slides online. The slides will be online, the class will be recorded by video, so that also means, at least in the first 3-4 rows, if you can keep the noise down while it's recorded, it's a good idea, first of all. Otherwise, you might actually be heard on video when you don't want to. Secondly, it'll make it easier for everybody else who can't be here in the class to actually listen to the stuff online. It'll go up on YouTube. The quality will be whatever YouTube makes out of high definition recording, which is not very much, but it'll be better than nothing. So with the video and the slides online, you ought to be able to catch up on things in case you can't attend the class. That might help. Okay, now, so for those who've never heard or seen of me, I do machine learning at Yahoo in Santa Clara, and so I'm there part of the machine learning team. Before that, I was in Australia at the Australian National University, and we ran a machine learning team there. And what I'm teaching today is probably a bit different from the type of machine learning that you would have seen if you, for instance, picked up like a Learning with Kernels book or something like that, or a book that's out of my past papers. It's a lot more systems heavy, a lot more how can we design the algorithms in such a way that they're actually applicable and implementable. And fortunately or unfortunately for that, you also need to know what the underlying hardware is capable of doing. So this first class might be a little bit rough on some of you, because we're basically going to do only systems, nothing else. So don't worry, we'll get to the proofs and the math and all the beautiful things later on as we go along, but you need to know what things your algorithms will be running on. If you don't know this, you will inadvertently design things that are really slow, have poor performance or anything. By the way, as I found out, I'm not the only one teaching a class of this or a similar form. There's John Canny, who's teaching I think a lot more applied with lab and experiments and so on class on more user modeling, and I think he's oversubscribed by a factor of 1 or 2, possibly more. So I don't know whether you'll get into his class or not, but yeah, so that might give you something even further on the applied end, I guess, if you want to do this. Okay. So now, before we can actually get on to the equations and the actual subjects, let's look at a few basic administrative parts. And well, the obvious thing is the class is Tuesdays from 4 to 7. If you hadn't known that already, you wouldn't be here. The one thing that I found out today is where my office is going to be. So it's in Evans Hall, room 418. That's one of those windowless offices. And I'll have meeting time from 1 to 3 p.m. So if that time doesn't work for you, I can possibly maybe make some exceptions on a need-be basis, but it basically means you'll have to drive down to Santa Clara and meet me there at Yahoo. The reason for that is very simply that Yahoo pays my day job, so they expect me to actually be there. And so if you want to meet me at some other time rather than this time window, and I understand it's maybe not so easy, you'll have to drive. Sorry about that. So the tutor we have, or GSI, we have one brave guy, Dapo Omidiran. I hope I didn't butcher his name too much. He's the guy hiding over here in the back. And so he has a lot more experience with classes than I have, and that's a good thing. So he will help me to make sure this is all going to be a good and fun experience. Now, in terms of how we distribute the points, there'll be 20 points for the assignments, and I'll tell you a little bit more about how that works in a moment. For the project, you'll get 45%. For the midterm, 15. For the final exam, 20. And then for scribing, you get 3%. So now I need those 2 volunteers for scribing for today. For everything else, there'll be a sign-up list, and it'll be first come, first serve. Okay. Who wants to be my scribe today? Okay, you? Who else? Can you email your name to Dapo afterwards?
Sure.
Okay. Anybody else who wants to scribe for me?
Do I hear 5%?
No. No. We had it at 5% before, but then I was told that would be too generous, so. Okay, thanks. Thanks. So the good thing is you will get to use all the slides, and I'll be putting them online. That will help you. And the other, however, I expect the scribe's notes to be more detailed than the slides. Otherwise, they're pointless. So I will occasionally show a few proofs and stuff. So, okay, you have a question?
You want us to record everything that you wrote? And
No, no, that would be insane. Because for that we already have the video. But I expect you to produce a decent, coherent write-up. So I would say if you produce about 4 pages per hour, so that makes about 12 pages, 12 to 15 pages, that might help you. And the thing is, the equations that are in my lecture, if you use Keynote and LaTeX, you can actually extract them directly from that. You don't even have to retype the LaTeX. And you can actually extract a lot of content from there. I would ask that you do it in LaTeX, because it just makes much nicer equations. So please don't try Word. It just makes for awful things. Okay, so good, we have to scribe for today. Should there be nobody willing to sign up until the end, maybe we'll raise that point threshold to 5, but and that will be retroactive. So you will not be penalized for signing on early. Okay, so the exams will be without technology. I was thinking for a while, should we allow a computer or an iPad or a phone or whatever? No, you bring a paper notebook, 8 by 10 pages of a reasonable thickness, as in stuff that you can buy for under $5 in a store. Right, so don't bring this. Actually, you can probably bring it, but it won't help you because you'll spend all the time searching, so your index will be too big. So. Homework, so there'll be 5 sets of assignments, and well, you really want to do it yourself. I mean, I will not go after people who copy and cheat. I just want you to look at yourself in the mirror, and if you can look at yourself with whatever you've done, that's fine with me. I mean, if you try to do it the easy way, you're just hurting yourself for the final exam or the midterm. So, now, one thing, however, is you must drop off your homework in class. So by the end of the class, whatever is here on this stack will be considered homework, nothing else will. No late drops, no exceptions. You have a time window of basically 3 hours, right, to make it here to the class. You don't have to be physically present in the class. You can get somebody else to drop it off, it doesn't matter. Whatever's on the stack counts. Now, of course, occasionally stuff happens and you can't get your homework done for whatever reason. In this case, what we decided to do is we will count the 4 best homeworks out of 5. So that way, if you screw up once, no big deal. It doesn't count. Okay, so effectively, therefore, each homework done well is worth about 5%. Okay. Last thing with the project, well, you want to really do it well. and you get about 45% of the score out of it. And yes, you want to start early. Maybe not right after this class, but maybe right after this class you might already start thinking who to work with. More to the point, I want you to decide by the end of next week. So Friday next week, 5 p.m., you need to send an email to DAPO with the list, with the teams in which you're going to, team up. If you cannot find anybody, okay, we can help you find other people who also cannot find somebody. But there will be the Piazza message board, so I would probably use this and a few other places to actually discuss and see whether you cannot find somebody. Now, if you can prove that you've used that message board and that you couldn't find anybody, we'll take care of you, but I'm sure you can. Team size is about 3 or 4. No more than 4. If you're only in 2 and you really decide that you can pull it off, well, go for it, but it's going to be more work for you. So I would not recommend it. I think 3 is a good number. If you're looking for ideas, talk to me. Send me emails. I should have a Berkeley email address by the end of this week. I don't have it yet, so I cannot tell it to you yet. If you possibly can, contact me through that Berkeley email address. The reason is very simple, that this is automatically a filter for me to find out that this is about this class. So if for whatever reason you want to contact me otherwise, please do put at least the course ID into the subject, and I'll set up a filter and make sure these emails get the higher priority. Okay, good. So that was the man. There will be probably one more GSI. There is a tiny URL for the Piazza discussion board, and for the office hours for DAPO, there'll be a poll.
So you guys should probably fill out this poll fairly soon. I'm thinking Thursday or Friday, so just take time for thinking about emails from the office hours.
Basically, it's in your interest. If you want to have the office hours at a time that you actually will be able to go there, do it. And there'll be a sign-up list for scribing. Good. Now, so with that said, well, let's actually dive into things that we're going to do in this class.
Professor,
Yeah, sure.
could you go back to that slide for just a second?
Sure.
Okay, thanks.
Yeah. Yes.
Are this slide online right now?
These slides are not online yet. They will be online after the class.
Okay.
Okay. The reason for me to do that is such that you look at the slides up here rather than at your laptop. That's a very simple reason why I'm going to put up the slides after the class. And they'll be online on the URL. So this is going to be the alexsmoller.org/teaching/Berkeley 2012. All lowercase. So I'll write it on the left. And there will be also the videos online. So this is actually stuff that you should be able to find anyway already by looking at your schedule, at basically the class schedule. There is a note in it which has the URL in it. So it should be reasonably straightforward to find. And yeah, there'll be all the videos. Given that it's 3 hours, and 3 hours is way too long to consistently pay attention, I couldn't do it. I don't assume you guys can. And yeah, not just paying attention. Anyway, so we'll have a 5 minutes break each hour. And yeah. Unfortunately, I can't make a longer break because otherwise we'll be stuck here until 8. So, good. So let's get on with the actual content. And by the way, do ask questions if you have any, anytime. Because from your questions, I can gauge 2 things. First of all, whether I'm going too slowly. I mean, that I can tell also by people simply falling asleep and snoring loudly. However, it may also very well be, I mean, it's happened to me, don't worry. And you guys have probably seen that too at some point. So the one thing is that you can also, if you have questions and you ask them, I then know that certain things aren't very clear. And that through that I will go more slowly and explain things in more detail. So by definition there are no bad questions here. If something is not clear, it means I haven't explained it well enough yet, and it's your job, because I need your help, to ask me questions to make sure I explain it properly. Okay? Good, thanks. So I really need your help in that case. So what are we going to do? Well, we'll start with systems and some basic statistics. So to those of you who know systems, this first class will be, let's just say, very boring. Basically, you could probably teach that class better than me. I mean, I've tried to, synthesize the latest of, a whole bunch of areas from systems. So this may actually help quite a bit. But for those of you who are strong, have a strong systems background, this will actually be fairly straightforward. The next class will turn things around and we'll do some basic statistics. So those of you who haven't taken a good statistics class, I don't know how many of you have or have not, will find that probably reasonably elementary. I'll do things like prove various theorems to tail bounds and so on to make sure things stay a little bit interesting, and I hope the assignments will, well, provide some entertainment, but this will be basic stuff. But we'll actually need those tools later on throughout the class. I just want to make sure we all have the same common set of vocabularies. So then we'll look at an application of actually those first two areas right away, namely data streams and sketches. So this is something that you may or may not necessarily have expected in a machine learning class, but I think it's actually an important thing that those two areas are sufficiently well combined, because they use a lot of the predictive machinery, and actually already there you could think of a whole bunch of fun projects that you could do for your class project. Then we'll touch upon optimization, which is something, scalable optimization, that's at the heart of almost every very large-scale machine learning deployment. It's either optimization or sampling. Then we'll look at generalized linear models, so that is actually not just generalized linear models, but also kernel machines, various classifiers, regression tools, novelty detection, density estimation, all those tools will be covered there. Then we'll look more at kernels, regularization, how to do fast kernel expansions. Then we'll take a step back, look at an application of all these tools, namely recommender systems, where we'll basically use all those linear models, various loss functions that we discussed so far, and then add the matrix factorization part on top of it. Then the next part will be moderately brief, namely graphical models, because apparently a lot of you already did take Mike's and Martin's class. May I ask who took Martin's and Mike Jordan's and Martin Wainwright's class? Okay. Is there anybody who did not take it? Okay, that sums up to more than 100% at the moment. But okay, so I will go through the basics reasonably briefly, but I will still review them for two reasons. First of all, I want to make sure you're familiar with my notation, because sometimes the same technique in different notation looks rather different. Secondly, we'll actually need those tools very, very importantly later on when we look at solving them at scale. So this is something that probably Mike and Martin didn't quite cover in the same extent as what I'm going to do. So we'll be then bringing to bear all the tools from systems in this context, and actually I'll show you how to build systems that scale a lot bigger than pretty much anything else. Then in the end we'll cover quite a bit of applications and look at maybe active learning, bandits, exploration. So these things will depend a little bit on how quickly we get through the class. But there is no fixed content set in the sense that, well, consider this more an upper bound, and the amount of detail we'll go into in various parts will depend largely on, essentially, you know, how much content I can throw at you in a given amount of time. And yes, I can rush through things very quickly, but then you won't get anything out of it. On the other hand, if I go too slowly, you'll get bored. So this is exactly why I need feedback from you to be able to gauge it right. So the main application is going to be essentially for the internet. And for instance, if you want to do a startup, this will more than enable you to do things really well. And I can tell you that with a reasonable degree of confidence, because occasionally, you know, you get contacted by some nice random startup and they tell you about the cool technology they have, and in some cases it's very cool, in some cases it's just very cold. So so let me put it this way: with this stuff, you can probably do better than, okay, I don't want to pick a percentage, but than a lot of startups that are out there. Okay, good.
Also without this.
Fun?
Also without this, you're probably doing a lot.
Yeah. Yes, that's the other thing. Yeah, at least if you need to do good data analysis, stuff like this. Also, you know, in bigger companies, I mean, you know, if you want to work for us afterwards at Yahoo, that will help, you know. I mean, if you already know this before you join, then I won't have to train you up for something. So this is good. So, or if you want to come as an intern, or you know, want to go as for internship to Google, Facebook, Twitter, or Microsoft, or whoever else. Anyway, okay, we're digressing here. So let's start it with systems. So the problem is that the algorithms that we design run on actual hardware. And they are not idealized boxes, but they are real and faulty and messy, and we really need to deal with that. So if we ignore all of this, you run into a big problem, and I'll show you how big the problems might get in detail. So let me give you a bit of an idea of what we're going to cover. We're going to look at hardware, basically CPU, RAM, GPU, disks, switches, server centers. So one giveaway, okay, this is a question I won't be able to ask anymore in job interviews. One of my favorite questions for a programmer is, how fast is your laptop? And you would be very surprised how many programmers are not able to give me a good answer. My favorite was 1.5 megahertz. The guy did a lot of Java. So the other thing is, I'll need to talk a little bit about data. Now, data is like the kind of thing that you usually worry later. You know, here's our beautifully convergent algorithm, and then, okay, well, where's some data that we run it on? Well, actually not. Data is a fairly integral part of this entire process, because gathering the data, making sure it's up to date, the type of structure, types of data that you can actually play with, will heavily influence the choice of algorithms. And I'll show you a bit in terms of parallelization strategies, how you can actually, you know, distribute, load, work, and, you know, things like proportional hashing. We've actually managed to make a lot of progress by using techniques that are very common in the systems world for machine learning inference. And so this is why I want to show you exactly how they work. Then you also need to know a little bit about where your data sits. So Google file system or Hadoop file system, Hadoop, Ceph, and just a bit of background in RAID might help you with that. And then the end, processing. So a lot of people who tell me, okay, I'm doing internet now, I'm doing large-scale machine learning, so I ask them, what do they do? And they tell me, yes, my algorithm runs on Hadoop. Well, that's very nice, but that doesn't necessarily mean that the algorithm is A, scalable, and B, that you can use it. So Hadoop is a wonderful tool. It's basically MapReduce open source, and it solves a lot of problems, but it doesn't actually solve everything. As a matter of fact, it doesn't solve a very large set of other problems, and I want to show you a little bit what other techniques are out there. And then in the end, I'll talk a little bit about databases, essentially distributed key value storage. You may have heard about NoSQL databases, and this is more or less, you know, just the tip of the iceberg of what goes on under that moniker. So, hardware. So, essentially, if you think about it, you want to build, you know, a very large computer center. What are you going to do? Well, you can have, you know, one very fancy project, and I think this is, the system in China, and this is how the Blue Gene from IBM works. And basically, it's super high performance hardware, very customized, very bespoke. They sell maybe to 5, 6 of those 3-letter agencies, and it's very, very efficient, very high reliability. They might have 10, 100,000 cores, of which not so many will fail. And, well, this is all very great if you have essentially too much money. On the other hand, if you want to get the maximum performance at a given budget, then you're much better off going for consumer hardware, or at least consumer-grade hardware. That doesn't necessarily mean that you're going to use exactly the same configuration, but you're basically going to use pieces in your system that are being sold by the millions, maybe hundreds of millions, maybe billions. So why would that matter? Because if it's sold to a mass market, it's very cheap. It's usually also very power efficient. For instance, if you think about all the mobile chips, they have to be very power efficient because otherwise people just get upset if their phone battery dies. They do not necessarily have to be amazingly reliable. So I don't know how many times per year your laptop breaks. It might be once a year or so. So then the point is good. You can't really get the very best reliability in hardware. Maybe we can design algorithms where we use software to fix the faults in reliability in the hardware. And just, you know, you deal with it. So, to give you a bit of an idea of what's going on. Suppose we have, you know, we want to get 1 failure per year and we have 1,000 machines. So basically once a year our entire system goes bad. Well, that's not a very good thing to happen, but, you know, for some not so critical environments you may very well be willing to tolerate that. So let's assume that, you know, we have things like hard drives that are failing, and, you know, let's just make a simple Poisson approximation, you know, at the tail of how those things fail. So that's a Poisson distribution. I assume most of you would have seen that thing before. So the assumption is that, you know, the failures are not distributed like, so the infamous IBM Death Star from, I think, about 6, 7 years ago, where very quickly, fairly deterministically, things would fail after a given runtime. So I'm assuming that at least I don't have anything that's really maliciously bad, like really wrong in the system. So then, you know, the good thing is that the Poisson rates of independent random variables are additive, so we can just combine it. And so the point is, let's just look at what happens, you know, how much time, or basically, you know, how our error probability behaves depending on how many faults I can tolerate. So the goal is somewhere to get, you know, 1 failure per 1,000 years per machine. That would, you know, mean that we really over-engineer this. Most computers will not be in that regime, and that would make the hardware really expensive. So instead, if we can tolerate k faults, then the probability that this will, you know, happen is now, you know, the probability that the faults will be larger than k is just very simply 1 minus, and here's the sum over the Poisson tail, so summing from n equals 0, which is no fault, up to k faults, and that is now the probability that, you know, things will go bad. And of course, the larger k is, the better my system, in the sense that, well, if I can tolerate a very large number of faults, then the probability that my system will keep up and running is higher. So to make things a little bit more explicit, I just plotted this function here for different number of faults. So that's no fault, this is 10 faults, and let's say I have a given quality of service level here, and this is the Poisson rate. You can very clearly see that, you know, for no faults, I'm way further down here on the left-hand side rather than if I can tolerate 10 faults, I'm definitely further on the left-hand side by more than an order of magnitude. So, by just so you can clearly see that you will actually get a boost that is larger than the failure probability that you are willing to tolerate if you're in the low probability regime. Yep?
Is the Poisson distribution realistic for the errors?
No. No, I'm just using this to give you a very, very rough idea and motivation of why this is not a horribly bad idea. So, very good question. Is the Poisson distribution realistic? Well, for some things it may very well be. So, apparently hard drives, at least reasonable hard drives without systematic flaw, don't change that much in their failure rate over time. So it seems to be an urban legend that they fail very much with that they have a high probability of failure initially, and then it drops off and then it goes up again, and that actually turns out not to be the case. There is, to my knowledge, a nice paper by either Microsoft or Google where they analyzed the failure probabilities of their hard drives in a server center, and they did not find this. So I think they actually got a best paper prize for this. Okay, so well, as a matter of fact, sometimes things are correlated. So this is a really cool slide from a talk by Jeff Dean. So Jeff Dean is, basically a senior researcher or principal, whatever at Google. There seems to be a list of jokes about him which go like the computer science equivalent of Chuck Norris. So if you search for Jeff Dean and jokes, you'll see it, and it sounds he sounds like to be a fairly intimidatingly good guy. So in any case, this might give you a little bit of an idea of the types of failures that you will see. So it's not just individual disk failures. So therefore, yes, the Poisson approximation is a horribly bad approximation that I just showed you, but just to give you the idea. But you might actually, so these are numbers from Google from a couple of years ago. I don't know how much they are still the same, but in half of all new clusters, half of them will overheat once in the first year, and then you lose all the machines for 1 or 2 days. Or some power distribution unit will fail, and then you lose maybe 1,000 machines right away. And okay, I don't need to go through all the details, but this will give you a little bit of an idea of the very different types of failures that you may encounter. So the bottom line being, if you actually design systems that are meant to be up and running most of the time, you will really need to be able to build algorithms that are able to deal with this type of faults. And I'll show you some ideas on how to do this. Okay. So before we go into a lot of the fault tolerance part, let's briefly look at CPUs. And so I'm just going to the various pieces of hardware in a system. So apologies to all the statisticians here. I know this is something that you will not have expected to see in a machine learning class, but you actually need to worry about it. And if you worry about it, you can design much faster algorithms. So the CPUs by now have maybe about 4 to 8 cores. The number is bound to go up. 2 gigahertz is a reasonable number of clock speed. And, well, you have several levels of internal cache. I'm not going to go into the very details, but something in the order between 8 and 16 megabytes is probably not an unreasonable number. Why does it matter? It matters because if you have data structures that fit nicely into the cache, the algorithm will just go that much faster. The other thing is they tend to have vector processing units, and that means that a lot of the hype that you have seen about GPU computing, it's not just hype, there's actually a lot of good things to it, but a lot of the speed-ups that you could get through GPUs, you can now also get through your CPU. Because they've moved a lot of those fast vector processing units into the CPU, the main difference now being only really the memory bandwidth. To give you a bit of an idea why you care about things like cache, the memory interface will give you between 20 and 40 gigabytes a second throughput. I mean, those numbers can be off by a factor of 2 depending on which piece of hardware. But the internal bandwidth within the CPU is easily over 100 gigabytes a second. And, you know, a reasonable thing to think about is that you will get easily over 100 gigaflops, sometimes, you know, maybe a teraflop or so for matrix-matrix multiplies. Now, matrix-matrix multipliers are interesting beasts because they combine things about how fast the memory interface is, how your cores are used, and so on. So Catherine Yellick, I think, did some really cool stuff with something called OSCI, how to multiply sparse matrices. So I don't know whether she's teaching a class, but you might be able to find out more things there. Quite often by now they have an integrated low-end GPU, so you can definitely do a lot of GPU computing on your CPU. Well, why do you care? If you get an order of magnitude speed up by just writing your code slightly differently, you may want to choose different algorithms which are, you know, maybe slightly worse, but then you have specialized hardware for that. Memory, well, you basically get, you know, those 10, 20 gigabytes a second throughput. So why do I write 10 gigabytes here? Because it's per bank. The one important thing is that sequential and random memory access have very different characteristics. We found out about it once the hard way. So this was running code which we first implemented, you know, just tried it out on an old MacBook, you know, by now probably about 4 years old. And then the server was a, well, FBDIM Xeon, so it had a specific memory architecture. And all of a sudden, the code which ran on a high-end server was a lot slower than on the laptop. And we first didn't know what was going on. Basically, the latency, because it used a lot of random memory access, killed the performance of the code. So random memory access will cost you at least a factor of 10. That's the important number to remember from that slide. GPUs, if you have a lot of computing to do, they're good. You get about 512 cores for 200 watts. That's a much better deal than the 8 cores for 100 watts that I showed you before. But the cores sometimes have a fairly non-trivial structure. You need to worry about threads and warps and how you synchronize stuff and so on. Basically, you get about 1 order of magnitude more processing power, but then you have a lot less memory, and the main bottleneck is really going to be how do you push the data onto the GPU and pull it back out again. So in some cases it pays off to design algorithms which actually use a cascade of those memory interfaces. We just did that, and then with a very simple piece of code you can actually, well, for instance, beat things that got best paper prizes at KDD fairly easily. Last part in it, hard disks. So essentially there are now 2 different kinds. I mean, there are the cheap and lumbering beasts which give you a decent bandwidth, like 100 megabytes per second for streaming is pretty good. But you will be essentially unable to do much in terms of random access. So 5 millisecond seek time is, so in other words, 200 operations per second is a reasonably optimistic number for your run-of-the-mill hard drive. On the other hand, if you buy a solid-state drive, then 50,000, maybe 100,000 operations per second is quite realistic. You go up by 1 order of magnitude in terms of storage price, but you gain about maybe 3 orders of magnitude in terms of you know, random access. Trick question for you: why is it the case? So think about that random writes on SSDs are faster than random reads. Okay, I'm not going to answer this now. You think about it, and it has actually a very beautiful answer. But you need to think about how they actually do the writing. Now, the last thing is, well, those machines, if I have a cluster of them, they don't just live in one very homogeneous network. They are actually hierarchically arranged. And if you ignore that, you pay dearly for it. So why would you not take, you know, 1,000 machines, build one big fat master switch, and have everything hang off it? Right? I mean, after all, this would be the best thing you could do. The problem is that switches actually require, you know, the bandwidth that you need on the backplane will scale linearly with the number of machines that you add. And then you need to add proper log terms for all the collisions and so on. So in other words, those things get ridiculously expensive. So you need to handle very high data rates. Which is why it turns out that about 48 is the magic number. And so you have switches of maybe 48 ports, maybe one uplink, and you have your machines inside one rack, and then you combine them. Maybe you have more than one switch per rack, but that's sort of the idea. So what this means is that your algorithms, if you can, should be, first of all, machine local, and then the rack local, and of course, server center local. So here's the concluding slide for the hardware part. Numbers that everyone should know. Well, I wouldn't claim that I know all of them, but at least by now you know where you can look them up. And I think they're useful numbers to look up if you design a very scalable algorithm. So if at some point you have the task of building an algorithm that works on a database of maybe 100 million users, and you have a certain machine budget, before you actually go implementing and then feel very sad about it because it doesn't perform, test it with those numbers, do a few back-of-the-envelope calculations to see whether, your hardware specs actually allow this. And to some extent, this is a very fun thing, because in that case, algorithm design is more like solving a puzzle, because in the end, you're going to be able to solve it. So basically, assume a solution exists. And all the hardware constraints very effectively constrain your search space such that you fairly automatically find the right solution. So it's kind of a nice thing almost, once you think about it this way. Okay, any questions so far on the hardware? Okay, some people have started falling asleep. Let's move on to data. Are there any questions? This is really just as a background such that you know what your systems will be running on. Okay, big data, everybody knows that there's a lot of data. It's not just on the internet, but McKinsey apparently paid somebody to compile this list, and you can look at it at some point, but basically, yes, you're not going to get only terabytes, you're going to get petabytes. This is probably a slightly more immediately useful list for you. So here, I'm not going to go through all of this in detail, are some data sources that you may have to deal with if you're working with data on the internet. And you can download the slides and enjoy reading them. The color coding means the following thing. Anything that's green, you can probably get without signing away your soul. Everything in purple, you would probably need to join one of the companies or at least sign an NDA or do something else. So if you want to work on the purple problems, come and work for us. For Google or Facebook or Microsoft or anybody else. Now, here's something that might be slightly controversial, but actually by now it's quite doable. So, if you suppose you want to crawl the web. So 10 billion pages are going to get you something fairly reasonable. So 10 billion reasonable quality content pages, if you have a search engine that has that much data, I mean, it's not going to, become a world beater, but it's going to give you pretty good results. So let's say we only store the text information, so it's about 10 kilobytes per page. So we have about 100 terabytes. That's actually not a big deal. I mean, by now you can buy 3 terabyte disks. So with 30, 40 disks, or maybe $10,000 for disks on EBS for a month on Amazon, you can store this. So the prices are about 2-3 months old. I don't know whether Amazon reduced them in the meantime. Now, we actually also want to process all of this, and let's think of very simple algorithms, which only take like 10 milliseconds a page. Okay, so we want to process them in a day. So I can, probably afford about 1 to maybe 10 million instructions per page. So you can actually do interesting things with it. You can probably categorize the documents, extract a few named entities, maybe relate them to a few other things, but that's going to be about it. That will cost you about $20,000 on EC2, and I'm simply assuming that you're going to pay about 68 cents an hour. If you sign on for long term, you get discounts and so on. So this is just really ballpark figures, and those numbers are likely to decrease. What's going to kill you is essentially the thinking of the data. So it costs you a lot of money to actually transfer data. The good thing with Amazon is you don't pay for data transfer incoming except for requests. But let's say you would have to pay an ISP maybe about $10,000 a month, or EC2 might be something similar. So, it takes you maybe a day, so 300 milliseconds page round trip, so that costs you about maybe 1,000 servers for a month, and they don't have to be particularly good, but that will cost you $70,000. So the point is, if I just could get all the raw data and just transfer it, it would be easy, but I actually need to go out, talk to that server, request the data, and pull it back in. And those servers may not always be the fastest, so this is why I just picked this number. Okay, so these are all hypothetical numbers, but at least a small startup could easily get itself a reasonable snapshot of the data on the web. Now it gets a little bit more tricky, namely the identity and graph information. So, for instance, Facebook is fairly open in revealing that network structure. I don't know whether they still do, but there were a couple of scripts that would basically go and crawl the OpenID graph. Then some other places like Twitter are fairly liberal with crawling the content of the tweets, but not so much in terms of getting the graph structure. So they have different business models. Some places may not want to reveal it at all, but a good number is so 100 to million to maybe a billion vertices is what your graph will contain. So you might wonder, why might you end up with so many of them? Well, sometimes users come along and they have duplicate, triplicate accounts, and they sign on with different ones. Sometimes they, just don't sign on, and you just get the cookie by which you track them, and you may actually want to, identify users nonetheless. And then it depends on your company policy whether you're allowed to do that. There were some recent lawsuits against Facebook about Facebook tracking users even though they said they shouldn't. And it's essentially stuff like that where you need to be careful. And this is why you may end up with a considerably larger user base than what you actually have. If we wanted to crawl Twitter, that would be a bit easier. You can do it for maybe about $10,000. So let's say they have about 300 million users. Per user who actually signs up for your service, which provides something else, maybe dancing hamster or whatever, you can issue about 300 queries per hour. Now you can get about 100 edges per query and 100 edges per account. So basically you can get 100 tweets per request and also 100 followers and 100 followees. I might need about 100 machines for 2 weeks, and that, crawl it at the reasonable rate to get tweets, in links, out links. And if you do the math and just go through the similar numbers as what I showed you before, it might cost you about $3,000 on EC2. And then, similar for network. And so the big issue why most of us here can't just do that is because we don't have a service that has 10,000 users who have a Twitter account signed up with an app key for you, which allows you then to go back at Twitter and actually crawl their data. But I've heard from some sources that Twitter crawls are available for a few $10,000. So given that reasoning here, that's not unreasonable. So, but those are the data sets that you would not be allowed to use. User-generated content, well, there's plenty of it. If you actually want to, crawl pictures from Flickr, well, go for it. Then there's things like Tumblr, Discuss, which is a lot of user-generated content. So for instance, also the Piazza system by which you comment would allow you to do interesting profiling about each of the users who post things there, right? So if, for instance, somebody answers a lot of questions, there's a good chance he actually knows stuff. Or maybe he's completely out of his depth. The amount of content that's being uploaded on YouTube, for instance, at the moment seems to be something in the order of 40 to 50 hours of video per minute. So there's a lot of user-generated content, user-generated data, and this number is going to increase. One number that I don't think will increase quite as much is the number of messages. So there we are, I think, a little bit closer to saturation. I mean, you're not going to write more than 10 emails a day on average. And the number of people on the planet is not growing at a rate where we'll need to worry about it in terms of our systems. So maybe a couple of billion texts is a reasonable number. The problem is you can't really get that without an NDA. So that's a big no-no. You would pretty much have to work for one of the internet companies if you wanted to work with that content, or one of the three-letter agencies. They probably have a lot of the data too and a lot more things. And I wouldn't know. User tracking. So if you've never done this, install something like Ghoster in your browser and you'll see what happens. So Facebook, for instance, actually says that they share the data with third parties and they delete it from backup after 90 days. Google, well, says anonymous data is shared and they don't tell you how long they keep the data. So I don't know which one is more evil or less evil. I think they're about even. So the point being, there's a lot of tracking. The New York Times, I think, at the moment has maybe about 10 trackers running. Why would you do that? So for instance, if you come to my homepage, you will also encounter 2 trackers. Well, to some extent, so the one is Google Analytics, the other one is Quantcast, because it gives me some idea of who comes to my page and when and how often. Doesn't identify anybody, at least I can't identify, but of course, Quantcast and Google in that case can. Well, why would you do all of this? I mean, why would I want to know that you watched The Dancing Bunny yesterday? Well, because then I can recommend you content. And, well, this is an example of Netflix content recommendation gone badly wrong. Basically what happens is, well, yes, this is all stuff that is recommended to me. This is what happens if an entire family shares movies, and so you have a mix of children's movies and all sorts of other stuff. I don't know. Basically, this is a lot more accurate. This is, you know, book recommendations, and it turns out that 2 of those I actually had sitting at my desk, and I was thinking of getting this one. So there's, you know, this actually tells you that probably the Netflix recommender system isn't so great in the sense that it doesn't actually distinguish between the devices upon which the content is being replayed. Here's another example of content recommendation actually in 2 ways. So this is a spam folder, and well, first of all, the spammers want to do effectively content recommendation for me. They might think that I'm feeling inadequate or I need an additional degree, so they will send me content that's targeted at me. At the same time, the spam filter is effectively also doing content recommendation and decides, well, no, actually this is something I probably don't like. So if you think about spam filtering in this context, you realize it's a lot more than just a binary classification problem. And, well, why is it challenging? Well, we actually have a monstrous parameter space. So let's assume we only want to have like 25 parameters. That's 100 bytes. Then for a billion users, that's already 100 gigabytes.